Alright, hello everyone. I'm Professor Caudill, and I think yesterday we ended around here. So we had some learning, some reading, assigned reading we had to do, McCullen's and Pitt's paper and the Rosenblatt paper. So I have the McCullen and Pitt's paper. I wanted to kind of show what I've highlighted. Um, so one thing I highlighted was this: to each reaction of any neuron, there is a corresponding assertion of a simple proposition. So that's he's going off of, or they are going off of, um, the idea that all neurons are either firing or not. So I was thinking it kind of makes sense with like the sigmoid function. Sigmoid is going to kind of put something between the value of 0 and 1. So think of for each neuron, each individual neuron as voting, then the sigmoid function kind of takes like a majority vote. So the next thing is the cold object. This whole paragraph I found interesting. I don't really understand the syntax here. It's borrowing from Russell White. It only cites like 3 papers. So yeah, if cold object is held to skin, so basically what they're doing is they're saying neurons that feel temperature, they assign neurons to the actions of the receptors. So it's kind of drawing, kind of connecting, like it's like a simple scenario of turning neurons into like a logic gate. Okay, and the next one is the phenomenon of learning. So this section I found interesting. The phenomena of learning, which are of a character persisting over most physiological changes in your nervous activity, seem to require possibility of permanent alterations to the structure of the nets. So Rosenblatt, I think, builds on top of this. Um, they're taking like an empiricist, physicalist approach to the brain, where um, they look at memory, and they view memory as not information being stored in like a hard drive, like a computer. It's not stored in cells or anything. It's arguing that the memory is stored in the actual structure and the connections of the neurons. So basically it says memory is it's kind of like a living system. So learning means you're actually changing the structure of the network. So for example, if you learning how to throw a ball, then the neural pathways associated with throwing the ball might get strengthened. Or if you have several techniques to throw a ball, the one that lets you throw it the furthest might get reinforced more. Um, Next one is no theory. I found this paragraph interesting. There is no theory we may hold and no observation we can make that will retain so much as its old effective reference to the facts if the nets be altered. So it's saying that, so I found this interesting because it basically says that it's kind of arguing against um, some epistemologies. And it basically says it's like it's very it crosses into like a lot of philosophy that I've personally been interested in. It's hard to put it exactly into words why I found this um, powerful. Basically we only know as much as the structure. If we don't know the structure, then we don't really know anything. I don't know. Trying to put it in simple terms. So the thing in itself, so that's very Kantian thing to say is the thing in itself. So if it's to think of it like quantum physics, where when you observe a particle, the wave function collapses. So it's kind of like that with the human mind. As soon as you observe it, it collapses into a point. So what this is saying is if you look at the mind, if you try to make the neural net of the mind something like deterministic, like you can know what every point is doing, then it becomes unknowable because you're missing out on like the dynamics of it. I feel like I could word it better if I spent more time on that. It's kind of difficult on the spot. So that's all the highlights I have for that Colin Pitt's paper. As far as the perceptron by Rosenblatt, I didn't get all the way through it, but I did find, especially like the graphs or the pictures that he adds. I found those to be quite appealing. So I'm pulling up what I highlighted here. So formation is retained. Okay. So whatever information is retained must somehow be stored as a preference for the particular response. So whatever information is retained must be stored as a preference for a particular response. So this is I think he talks about two types of memory. So we look keywords the first, and then we're gonna look for the second. The alternative approach. Okay, so the first, the alternative stems from the tradition of Hazard's guess. Okay, so I think he declines this. I think he specifies oh no, he prefers the alternative. First suggests that storage of sensory information is coded or stored as a one-to-one mapping. So I think he disagrees with this, and he prefers the alternative, which stems from traditional British empiricism. So British empiricism, I think of it like Stanford's physicalism. Like it's basically saying there is an objective world, everything is made of physical matter. Everything is physical, even British empiricism it would say God is not existent, like this rejects like anything supernatural or metaphysical. Um, so I found this to be really informative. Whatever information is retained must somehow be stored as a preference for a particular response. So memory is like a preference. And oh, I'm sorry. Theory to be okay. So he explicitly says the theory that we use is a connectionist, or I say physicalist. To answer these questions, the questions are things like how is memory stored, what are the underlying things of the cognition. It's like in the beginning of the paper. Um, what else did I highlight? The perceptron, the actual design of the perceptron. Okay, so I highlighted this meshed. Okay, so I found this section to be interesting. The perceptron, which is his hypothetical nervous system, as he says above over here. The theory has been developed for a hypothetical nervous system based on physicalism, or a hypothetical machine. So he's equating nervous system or the or the biological neural net as a machine. He's making an analogy, or he's making a hypothetical claim that they're equivalent systems. The artificial and the biological are equivalent, and he's saying this equivalence is called a perceptron. Perceptron is designed to illustrate some of the fundamental properties of intelligent systems in general. So the lectures I've been posting have been in a playlist called Intelligent Systems Engineering. So I felt that this highlighted kind of the core of where the course or the lectures are, the direction I want them to go in. So the perceptron is designed to illustrate some of the fundamental properties of intelligent systems in general, without becoming too deeply enmeshed in special, unfrequently unknown conditions which hold for particular biological organisms. So, another word, I know some people dislike the term AGI, artificial general intelligence. So, and I think I'm being more sympathetic to the dislike. So, the quest is to understand general intelligence. So if you have AI, and then you have BI for biological intelligence, then GI is going to be in the middle. Okay. General intelligence might not be made of silicone. Biological intelligence, no. AI might not be made of cells and proteins and potassium and sodium ions. And BI might not use pure electricity or silicon, but the intelligence between these two intelligent systems we can call it GI. So one kind of interesting thing is by studying AI and studying BI, we can kind of understand what's going on in the middle. And that's where the good stuff is in one point of view. Okay. So next quote I found, if Okay, so all or nothing basis. Okay, so this I found interesting. If the algebraic sum of excitatory and inhibitory pulses intensity is equal to or greater than the threshold theta of the A unit. So he's referencing this graph up here. Then the A unit fires again on an all or nothing basis. So, and I think he goes into how these connections are built. I think some of them are at random. Okay. The connection random, yeah, so he specifies random connections. Can't read this. Socialized. Associated? Is it associated? Or the localized? Okay, I think it's saying localized. Okay, so let me redraw this. So he's saying localized. No, the connections are localized. Localized connections. And then you have 2 layers of random. So let's say doesn't have to be left to right, I guess. AI, so this is projection. This is your retina. Or this is the retina of a general intelligent machine. This is a projection. This is the association. So this is random. Random connections. And then from here we have response. Okay, and so these are also random connections. So he has 1, 2, 1, 2. So if you are paying attention, you'll notice that R2 has 3 connections versus the others. So what might that mean? Obviously, he's going to learn R2 more than the other responses. And this layer has feedback. It's also random. So, I mean, these are early ideas. You don't need, like, I could probably be fine not going into this kind of depth, historical depth, but out of personal interest, it helps me learn to have like a strong historical background. I'm sure we could build cool stuff by skipping all this, but personally, I like the history. So let's move on to the next point I highlighted. These origin points, origin. These origin points are scattered at random throughout the projection area. So I found it interesting that learning has like a random element to it. And the most interesting. Okay. I found this statement also interesting. The most interesting models are those in which cells are assumed to compete for metabolic materials. The more active cells gaining at the expense of the less active cells. So there's a lot of surprising intuitions. One say general intelligent neural nets. First, randomness. Is an interesting factor, and then two, there's competition. I want to say like survival of the fittest, but I think competition might be a better word. I should probably spell this right. Competition. So those are two things I found interesting in these papers so far. I'm about halfway through the Rosenblatt paper, so I'll probably finish it today. And then there's also the I recommend everyone to purchase this book. I don't think it's this one necessarily. Yeah, so I bought this one. It'll be here in like 2 days, 2 or 3 days. So this is, I think the Wikipedia says this is one of like the fundamental. A lot of the stuff is slightly outdated, but I heard or I read from Wikipedia that Minsky's ideas of frames are still used quite a lot. Not sure exactly what they mean by frames. I'm assuming it's something different from the computer networking term. Yeah, I bought this book. I recommend you guys to get as well. It's 300 pages. Should be able to knock it out in a day or two. So that's it for the required reading. I guess we can kind of return to where we were. So we got here. Oh, and I think one important thing is this book. So Minsky's book is arguing or is improving upon Rosenblatt's invention. Oh, I should have showed you some of the graphs, but you can probably find it yourself in the Rosenblatt paper. But they have some cool diagrams. Anyways, Everything that they showed were single layer devices. So I'm not sure what they mean by single layer devices. What Rosenblatt is describing is kind of multi-layer. I mean, you have one layer here, one layer here, one layer here, and then maybe three. It depends on like, I'm not really sure what this textbook means by that. Um, is there a way I can try to make this bigger without cutting it off? Okay, I hope you guys don't mind if it's cut off a little bit. It's a little bit cut off, but okay. So yeah, basically some math functions this model can't work. I'm not exactly sure what they mean by single layer. So that's maybe something we can learn by actually reading the book Perceptrons. Okay, so now we have more assigned reading material. Perhaps the most pivotal work in neural networks in the last 50 years is the multi-volume parallel distributed processing by James McClellan. Okay, so let's find that. Okay, is there... Looks like Stanford has their own version. No, this is it. It's chapter 1 though. So, do they have the full book? They do. Uh, only some. Volume 1, 1, 2, 3, 4, 5. Volume 2. Okay. So, yes, I think we should download all these. This is a full, what is this? Setting up a PB software on PC. Okay, that looks like an old document. 2007? Yeah, no thanks. Um, okay, so PDP perspective. So we should just go ahead and read all of these. Should take a week maybe. Um, if you guys want to find this yourselves. So I typed in PDP by these guys. Scroll down to the Stanford link. It's in the directory of JLMCC. So click here. Then you have to go up to the browser and then just take out chapter 1. So it just says /PDP and it'll take you to the actual directory. This is James McClellan online homepage, last updated December 2022. So it looks like he's still pretty active in the field. All of his papers is pretty impressive. So I'm guessing this archive takes you there. Yes. Okay, so yeah, we will have to download these 2 volumes. You can't see it, it's kind of cut off, but at the bottom here, this is volume 1, this is volume 2, and there's files you can click. opens them up, and they can download PDF. So I will download those. I will read those. If I can really geek out, I can probably read this volume and then finish the Minsky book by Monday. We'll have to see. So yeah, that's our next reading. That's our next assigned reading. People are smarter today because people are smarter than today's computers because brain plays basic computer architecture is more suited to deal with the central aspect of the natural information processing tasks. Premise of the PDP is it's using here. It's that traditional computer programs work very differently to brains. And it's saying because of this difference, that's why those old computers kind of trivial. Yeah, they're just close to the frameworks, how the brain works. So, in fact, the approach laid out in PDP is very similar to the approach used in today's neural networks. Okay. Book defined parallel distributed processing as required. Set of processing units, state of activation, output function, pattern of connectivity, a propagation rule for propagating patterns of activities through the network of connectivities. Activation rule for combining the inputs impinging on a unit with the current state of that unit to produce an output for the unit. That's a mouthful. And a learning rule whereby patterns of connectivity are modified by experience, environment in which a system must operate. You'll see in this book that modern neural networks handle each of these requirements. Okay, so this is why this book, and yeah, so McClellan, props to him. He kind of just open sources his books. That's very nice for us. Only problem is this is just part 1 of chapter 1. I don't know if there's a part 2. So the actual book, the $60 book you might buy, might have a little bit more, but I mean this was last modified in 2016. So I think this directory is a fair chance. So yeah, it's just this. If you need to find this, stanford.edu/ curly JLMCC/papers/PDP. All right. So in the 1980s, most models were built with a second layer, avoiding a problem that was identified by Minsky and Poppert. This was their pattern of connectivity among units. So 80s and 90s neural networks, I think of like the AI winter around the 80s and 90s, but they're actually getting real practical projects during that time. Here again, a misunderstanding of the theoretical issues held back the field. In theory, adding just one extra layer of neurons was enough to allow any mathematical function to be approximated. In practice, they are too big and too slow to be useful. So just the actual amount of computation was also a critical factor. It's not just, even if they had the theory, there would still be like the computation speed problem. All the research showed 30 years ago that to get practical good performance, So the trend has been that they started with this one layer. You cannot get all the. So if you're saying neurons are equal to propositions, okay, proposition, then for all basic uh, formal logic operators, one needs a minimum of 2 layers, okay, and practical AI uses, let's say, much greater than 2 layers. Okay. It's only in the last decade that this principle has been so it's only in the last, when was this book written now? Not sure when exactly this book was written, but recently it's just layers and layers and layers. More layers means more, I don't know, function. Okay, so what algorithmic tweaks allow neural networks to be trained faster and more easily? I did, the language model did tell me that the sigmoid function has kind of been replaced by the ReLU function. So I'm thinking that's one example of that. So these books and principles they show should allow us to build machines capable of perceiving, recognizing, identifying surroundings without any human training or control. One of the kind of ideals of our college is to build a competitor to the U.S. national intelligence community. I'm imagining like an intelligence community without any traditional humans in the loop. So thinking like the president of the United States is a human. Say he wants some intelligence on to make decisions, so he just prompts or he gets generated a presidential daily brief every day by an AI, and the AI got all the information from its own sensors. It gathered its own human intelligence, just everything, like just all the labor in the intelligence community as it currently is gets automated away. So hopefully this kind of pushes us further in that direction. So this book is what we want. This book. So I'm feeling hopeful for this book. I think we got on a rough start with the other book in this playlist, but um so Jeremy, again, I recommend you looking up Jeremy on the Lex Friedman podcast. This website is also fast.ai if you're unfamiliar. So yeah, this kind of hits home with us if you're somebody who would rather get your hands dirty building stuff than spending years learning abstract concepts. Then basically he's our guy. Um, so he not him as well kind of struggle with the math. Um, and we have the opposite of him, someone who's written 10 math books. Okay, so all right, so how to learn deep learning. Harvard professor David Perkins wrote Making Learning Whole. It's much to say about teaching. Basic idea is to teach whole game. That means if you're teaching baseball, you first take people to baseball game or get them to play it. You don't teach them how to wind, twine to make a baseball from scratch, the physics of a parabola, or the coefficient of friction of a bat. Paul Lockhart. So, another way of saying this, as I said in 2 videos ago, basically drilling the basics. Drilling the basics, as in like you're playing baseball. Um, uh, More or less, I would say. So they're gonna give us real examples. So again, this book's pretty hyping us up. I hope it lives up to the hype. As I said other lectures ago, I'm not going to watch any of the videos. They have posted videos. Some of the people, authors of this book, have made videos that go kind of walk them through. I'm going to abstain from making videos. Um, they're making videos on the textbook, just like as me, but I want to give my own unique perspective to their videos. So I respect this a lot. As until now, it's been a very exclusive game. They're making it open and letting everyone play. Um, you know, as far as like the free open source movement goes, that's a respectable position. So one hard part is getting enough, knowing if you have enough data in the right format. So format that comes to mind like .csv files, um, what stands for comma separated values. So it's just like a text file. So they believe in learning by doing. So this will be a very hands-on lecture series. So I wonder if they will say like what's the best way to use a website. I mean, they kind of just threw a bunch of links on the homepage. Um, I wish they would kind of. It's like I know everyone learns differently, but at least maybe like should I do chapter one in the book and then do the exercises? I don't see exactly a good like a clear correlation path. So this guy without I think Andrew Karpathy referenced this paper. So this guy does not have a PhD, and apparently he's been cited a lot. $5,000 citations. Okay, so this is also required reading now. 16 pages shouldn't be too bad. Um, okay, so remember our required reading is if you haven't read the what are their names? Um, Rosenblatt, McCullen. So our assigned reading is the McCullen and Pitt's paper, the Rosenblatt paper, Minsky's perceptron, okay, and so I'm done with this. I'm about halfway done with this. Minsky's book is in the mail. So until then, I'm going to read. So we're gonna read McClellan. So we're gonna read McClellan, and then we're going to read uh, Radford and Metz. Okay. Should be a volume. 2-volume book, 2-volume. Okay, so it's not a lot of reading. Two papers. I mean, these are short papers. So we have three papers. They're all pretty short. You can probably read them in like 3 or 4 hours to get through them. get through the papers, the books, and the 2 volume. Let's say 3 books because there's 2 volumes. Anyways, that might take you a week or 2 weeks. So you're sacrificing like a week or 2 weeks to really get a good foundation on like the history of the field, and that's probably going to be pretty invaluable, I would say. So applying this to a personal project, that would be interesting. I've kind of outlined some ideas in the like first 5 lectures of this playlist. Some ideas of mine. Again, it's easier said than done in most cases. We will get you using deep learning for your own problems. Okay, so one simple example would be like deep learning your shopping list. Okay, so maybe let's say like you input each week's grocery 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 list. Okay, and then if you have each week's grocery list, can you make a deep learning model on your grocery list? Um, would the whole inventory of the supermarket or the grocery store, the whole inventory be the a priori knowledge? Like, would that already be inputted into the system? Um, and you could also like input like a healthy diet as well. So a priori, you could do some deep learning as far as like actual diets go as well. Um, you learn how to use deep learning to solve your own problems at state of art actually within 30 minutes of the next chapter. So the next chapter is going to be pretty sick. Yeah, so this is not true. You can even like rent GP or like cloud computing that is dedicated to AI applications for like pennies. So you can borrow like a super fast GPU for pennies. So what sort of tasks make for good test cases? So don't be try not to be too ambitious. We are focusing on the basics. We are drilling the basics. Common character traits in the people that do well at deep learning include playfulness and curiosity. The late physicist Feynman, example, someone who we'd expect to be great at deep learning. Okay, so we know Jupyter. Jupyter's very easy. It's just an IDE, web browser based IDE. I love Jupyter. I haven't used PyTorch. I haven't used Fast AI. Um, so I'm gonna end it there. Next time we'll pick up on the software. And we're still in chapter 1, so yeah, I'm gonna end it there, guys. Pretty good video. Make sure you do the reading. I've certainly benefited just in the short amount of what I've read. The pictures really help in the papers, and some of the online resources I was looking at earlier. They literally copied and pasted from these 1950 papers. So yeah, thank you guys for watching, and I'll see you next time.